Okay, today I give you relatively new terminology for microgravity geology. That's it. Okay. It's going to be a new challenge for both human and robotic exploration. These are the objects we've been to and we are going to. This is Itokawa, it's Hayabusa's target, and this is International Space Station in scale. And this is 1989 JU3, it's a target for the Hayabusa 2 mission, which is bound to be launched next year. Okay, so nevertheless, this is just about half kilometers and it's a little less than a kilometer size asteroid. Whether you think it's big or small, it's it's a matter of relativity. But as you go along, especially for the space mining, it tends to be a closer target, which tends to be much smaller than Itokawa. For instance, Itokawa's got the largest boulder sticking on the surface, which is this 50-meter cross. So this is a little bit of equivalent to 2012 DA-14, which has passed inside of the lunar orbit a few days ago. So it could be catastrophic if you get frostbite and stuff. So doing mining, this is a chart from yesterday, taken by the Apache Resource Corporation for Interdisciplinary. But in my view, to do the asteroid mining, you these all 5 phases in sequences. The survey and where you go, and then once you decide the target, you investigate in remote sensing, and then you study about the physical structure, especially internal structure. And then you somehow have to land and start to do your physical activities. And then you bring the samples back to wherever target market is. It may be Earth or it may be in situ, rockets or spacecraft. So for the rest of the talk, I would like to concentrate on these 2 topics: its internal structure and landing mining. Of course, if you mine underground, that means it matters of how deep you go. But all we know about those pictures is only superficial appearance of the celestial body. So in order to understand the depth profile, there are various techniques to study. Of course, in larger ones, you have to go to much larger asteroid. But for these cases, these are too large for study. For the case of like 100 kilometers or less to a meter. Excuse me, this is 1 kilometer and this is a meter. Okay? So this is about the range we like to investigate. And then there are several techniques which has been only applied on the Moon, Mars, and others. And then it can be applied to such a dry solid body as asteroid. Radar sounder, tomography, seismic network, and border group in situ roving investigation, or fixed lander to study in situ. And these are something we haven't achieved yet for asteroid exploration, but certainly this is within the reach of that kind of technology for the future missions. And for those ones, which is like sub-meter cross, sub-meter information, these are usually subject to sampling and subsequent analysis. So this is like one example of possible hypothesis how it look like if you cut in half of the asteroids, like photos. And then some people believe that top surface must be accumulated with regolith or powdery things, or because these are grounded by meteoric impact and there's some gardening effect and seismic shaking. And then, however, those smaller ones, some are stopped in intermediate stage where the friction becomes dominant, so you can't go any further down. And then, therefore, the largest voids, which could give a macro porosity of 20 to 40% in typical asteroids, governed by those central portion. That's one way of thinking it, but we don't know, to be honest. Of course, then another way of thinking it is that these are key questions when you do. I think this doesn't matter if it's a small body, it's a moon or terrestrial, but it's all the same. But these questions are how to reach it, and then for the case of celestial body, how to descend and land, and enter us off, and excavate and contain, and how to examine which is good, and how to ascend and how to return. But those black and blue areas are something you have to deal with the spacecraft technology. And this orange portion is something you have to deal with some mechanics interact with the surface, such as sampling devices and stuff like that. These are just cartoons of concept, and some of them are coming from the current NASA studies, like 2020 Space Odyssey type pods or tethered wrapped asteroids, so quantified asteroids. And this is more old-fashioned version of this. But anyway, there are various ideas, but the important message is that you have to know your enemy. And then the most characteristics of your enemy at this time is microgravity. Okay, so this is another chart from yesterday. So we are thinking about a series of sample return missions, starting from Hayabusa, Hayabusa 2, and third generation. In parallel to our efforts, our American and European friends are thinking very similar trend. So now we are kind of blooming this type of things, and that is fundamentally important for asteroid mining if it ever happens. Okay, so that's my statement. Microgravity geology is a new challenge, a new research field of solar system science and engineering. Since my background is fundamental geology, so I just put it, the first fundamental question of formation of the solar system. But for the audience like you, that I say the second which is no one had witnessed the geological evolution of small planetesimal to or equivalent until Hayabusa saw it in the color. Because we never seen the processes like a centimeter rock impacted and becomes 2 centimeter rock. We never seen that. But somehow we had mechanism from dust, some millimeter dust all become all the way to the size of the Earth. So, of course, once it's coming to a certain size, the thermal energy or the gravitational energy take place. But before that, you may have to play with some other governing forces depending on the scales. Okay, so apparent similarity, those who present yesterday, I show you some similar, apparently similar landscape between Earth and Itokawa and Eos, but that not necessarily the same processes, same physical processes play a role. Okay, but we don't know which physics is in place. So that's something we have to find out, and we have to make a theory or hypothesis, and we have to test. So that's why then we need to create a new research field, which is microgravity geology, in order to better understand the evolution and formation of the solar, the asteroid and comets, let alone your mining places. It doesn't matter if it's human or robotics, because you need it both anyway. And then by understanding this, especially these two, and then there may be some knowledge can be also applicable to natural disaster management back on Earth. Okay, a few years ago, back in Japan, I set up this type of forum of microgravity geology research field, and this is a flowchart which starts from the data analysis on microgravity body, such from spacecraft data, and then we'll do a 1G environmental test like impacts or elastic wave attenuations, which may not be necessarily be strongly governed by gravity. Well, then I compare these effects by reducing the gravity by using some techniques such as drop towers and the powder flights. And also the granular convection in microgravity. or maybe hypergravity to understand a bit of physics, and then put it into simulations, and then we put into the new physical models, which creates apparent the geological features of asteroids. Okay, so the main focus, because this is a totally new field, but we have some handles to bring it in, because there are some neighboring fields which we can pull in. That is, one of them is impact study. The other one is vibrations, especially granular vibrations, and which leads to this granular mobility. For the case of the impact, it's called how large your crater is. You have lots of craters in Australia, and then you have to understand what sort of size regime you're talking about. Then the gravity and strength regime scaling law is varies, and then of course exact same impactor at the same size and same velocity, impact speed, you have robotic target or granular target. Consequence is very different. So for the vibrations, you have seismic efficiency and diffusivity dependent upon internal structure of the body. The granular mobility, you know the blood nuts effect. That's how effectively or unaffectively works in microgravity conditions. And granular convection, which we witness on the surface of the cloud, and dust levitation, which is sort of witnessed by the Apollo astronauts on the surface of the moon, and then apparently we some witness indirectly on the surface of the cloud. And of course, those will be feedback to development of new spacecraft devices. Okay, understanding the geology feature. Let's sound like that. Okay, this is a chart from yesterday. As I said yesterday, we have lots of characteristic geological features on this planet. The body train, gravel fields and breccia, sandy pond and landslides. And we have exact same geological feature on asteroid. But asteroid lacks air, water, and maybe volcanic activities. But still, we have apparently similar features there. And that it must be, so you have, by lacking water and air and volcanic activities, you have to have some external forces other than that. But before going to the asteroids, we have some knowledge about the physical property of the target. One of them is spin rate. A spin rate in size, and if you spin up so fast that the bonding force, if they are mobile, are actually disintegrated by centrifugal force. So therefore, this is sort of the centrifugal boundary there, and then so anything faster, this way, sorry, anything faster than this way is actually considered to be monolithic. So for the case of Itokawa and J3, these can be in the region of possible mobile region. But that's indirect evidence. And another evidence is a thermal measurement in red. Of course, you know those thermal inertia. It depends upon surface texture of the rock from 10 to 2000, coming from very fine, highly porous rocky level all the way to monolithic bedrock. And then we actually measured thermal inertia in Itokawa right there, and then these and moon, and Ceres and Eros indirect measurement. But nevertheless, that would sort of fit our model as well. So that's another handle. And then we have yet another handle that is meteoroids. This is very expensive experiment. We actually did a compressive strength measurement of Murchison meteoroids, and also some people did the Turkish-like. And anyway, these are the compressive strengths in order of less than 100 millipascal to 0.1 millipascal. It's a 3-order magnitude variation depending upon the type of chondrites, even within the carbonaceous species. Okay, by knowing that, we can actually make a cheap analog from concrete, and then we have monolithic and global and final levelness is a very crude asteroid simulator, because otherwise you can't start developing your sampling device. And then in case of extremely porous material, we just use those like spongy-like structure. And then this is a core, it's just a file core, and then those samples accumulated inside. However, it is also note that those porosity, 20 to 40% in average of the asteroids, may be realized by macroporosity or may be realized by microporosity. We don't know. So then, in case of the microporosity, then we still have like porosity roughly 40%. We can actually assimilate those similar ones by commercially available glass speeds, even like 5 millimeters and 500 microns. And then we do the same impact shots. And this is a reality. This is 3D microtomography images of single Itokawa particle. It's size of like 100 microns or so. And then, as you can see, these are two particles which looks at the sharp edges and then rounded edge. So we know some understanding of regolith of asteroid first, but still it's just only one asteroid. So we largely still depend upon astronomical observation and experimental efforts. And then, in order to do microgravity studies, we need some special apparatus. This is, in this field, microgravity field, we call gravity duration diagram, which is this one. It's very simple. You get logarithmic scale of gravity level and logarithmic scale of time duration. And then these are the typical gravity of celestial bodies in solar system: Earth, Mars, Moon, Sirius, Vesta, Enceladus, Itokawa, and J3. And then where they put it? These are sort of very crude plotting of respective possible geological processes on the surface of asteroids and comets. From the Gaussian and Brownian convection layer accumulation of ejecta and gravity-ness effect in dust aggregate Brownian surface mobility, non-gravity effect, which means like a comet gas jet, or dust levitation by electrostatic forces, and hypervelocity impacts. Well then, there are some facilities available to do some simulations. And the red one is all man-tended facility, so it can be restricted and expensive. And the other one is unmanned ones. It's much cheaper, but it's like much smaller and some other inconvenience as well. So nevertheless, message is that depending upon which target you are going to and simulate, you have to choose right apparatus. Okay, this is all kind, and maybe plus counter mass or low friction test beds, as well as underwater analogs, especially for the human train, maybe also good for long duration. Okay, this is just an example of how we use Hayabusa to development. We use mainly parabolic flights and drop tower for different things. This is a detachable camera, and these are surface robots, German robots and Japanese robots, and sampling device. So in order to develop them, we use lots of those apparatus as well. Okay, so in the last 5 minutes, I just quickly show you examples of what we have achieved in the past. Okay, for the case of high and slow velocity impact, of course, as I said, impact makes you grow or break. We don't know the boundary. So whether it's a disruption or the aggregates. And in that play, I think the scale and velocity plays a very important role. And that's why for us, we have a drop tower right there. And a 100-meter drop shaft back in Japan. And then within that, we have a vacuum chamber with leveling carbon in it, and then and it's fired as a projectile while it's descent, and it gives you 4.5 seconds worth of 10 to the minus 4 g, which is equivalent for surface gravity of the carbon. And then that will give you that, and then those craters in snapshots. However, up until this experiment, people believe that if you left at gravity, your crater is keep expanding because if it's a granular, and it becomes extremely large because of gravity strength regime calculation. However, what we discovered is no. The 1G impacts and the microgravity impact almost identical, which is quite surprised. And then what that means is that we are working on this hypothesis that by lacking the gravity, but however these 100 micron particle size, which is important to have cohesion forces such as frictions or even van der Waals force, makes a very big role in substituting against gravity. So, and also this Itokawa image, you never seen these unstable rocks or small pebbles sitting on the top of the larger ones. And we see almost identical landscape of the landslides on the Earth. And then we actually simulated a geopotential flow, which exactly matches upward movement of the rocks. And then that may be due to the seismic shaking, but the efficiency of the seismic shaking is dependent on internal structure, like I said before. And then there's only one possible example of that this pebble, rock may be missing amongst apart of the surface of asteroid while the Hayabusa is still. But this is still controversial, so I didn't publish it, but was doing it. But important thing is that you have to study about the wave attenuation of the internal structure. And that's something you can do in UNG, so we do it with attenuation, very simple attenuation acoustic experiment to see if we follow these things. And then if you do reduced gravity things, and then we do the resonance effect in 1G, 2G, micro G sequences, and then we can finally see that's it's governed by the gravity, which is fits for the formula. Dust gravitation is one of the most difficult portion. This is a non-gravitational effect, and many people work on it, like Shields et al. But the people can simulate launch of some micron particles quite easily by catching up the electromagnetic force of the solar irradiation. But it's extremely difficult to take the particles out in order of 1 meter in the surface above the surface. And there's no mechanism has been explained, and it's still working area. And then the other one is, okay, now you're starting with the intact, where you land, catch and go, or the blast. There are various techniques. Landing, for like case of Rosetta, which will land on the surface of the comet next year. And this is a similar concept from my American colleague, that they have harpoon and anchor and legs, wish you luck. And then, however, the Russian ones it's more like forcibly descent firing, and then they start on forwards. Although this spacecraft itself was not able to define. Or, okay, there are various other things. You just let it bounce and land. That's a strategy we use for our robots. Minerva and Mascot and Hayabusa 2. And we try not to bounce those artificial target marker, which is artificial lighthouse in the surface of asteroid, which we use for Hayabusa. And for the case of sampling, we just use only 1 second touch and go. And self-exposing as well. Okay, so that's how we did touch and go sequences in Hayabusa. And then by touching the surfaces, we have some understanding of stiffness of the surface. and some equilibrium for the temperature. And of course, there are various like steep impacts and L-class, and this concept, European concept, Don Quixote mission, and this is Hayabusa too. These physical interaction are also viable to study internal structure. Okay.
Go to your summary slide, please.
Okay. I think this is it. Yeah. So we have 3 areas to handle the microgravity geology, and there are a lot more people to be involved. But basically, spacecraft data, which is already started to be accumulated, and then experimental facility is something we have to develop more, and then the modeling. So those 3 all come together, and then it has become critical elements of small modeling research and also future money. Thank you.
I just wanted to say, Dr. Yano, that if I was a young person, I would be very excited about getting into this field.
Well,
I think it's
you're
fascinating.
not too late.
Thank you for that fantastic stuff. I've got a question that also relates more back to what you spoke on yesterday. You showed a diagram indicating flow on the low gravity of fine particles into those seas. What rate under the microgravity conditions are those particles moving at?
Of course, we don't know from the spacecraft data, because we only stay like 2 months, and only one possible movement, which is relatively large. But however, we actually studied that, and we taken a model, and we've seen some evidence of the terrestrial laboratory experiment. And the answer is it's extremely long period. I mean, compared to terrestrial landslides, which occurs in a few seconds and minutes. But usually, we are thinking about years of things. And then, however, the trick is that we think Itokawa-sized asteroids almost constantly reshaped by the impacts, whether large or small, or local or global. So, so there's a very few large impact occasions which jumbo total surface of the asteroid Itokawa, which only occurs in very, very infrequently. However, all those local movements initiated by local impacts are quite local.
So if you take an average rate, would these particles be moving at millimeters a year, microns a year?
Well, it depends, as I said, it depends on the size.
Yes.
Yeah. For the small size, which can be easier to move by the smaller seismic vibration. And so that means frequency is much, much faster. And I think that's why we see those apparent landslide features. Landslide feature means that larger blocks can stay higher and lower, and small ones stay lower. But that's because of the frequency of the movement.
Dr. Yano,
Yeah.
Itokawa is a rubble pile. Yet it's only 500 metres long. How small do you think we are going to continue to see rubble piles rather than monoliths?
That's a very good question, and I wish I could answer that. But I would say rubble pile today, which means 4.5 billion years after the formation of the solar system, it might be very, very, very small population in order of meters. But
In order of meters?
yeah, in meters. It's very rare, I must say, because usually the definition of lifetime of asteroid is impact frequency, and so the small ones get disrupted much quicker than the larger ones because of population indices of meteoroids. So that the meteor-sized asteroids, unless it's monolithic, are quite easily disrupted. Okay.
Thank you again, Dr.